Okay, so the other type of improper integrals come from discontinuities of the integrand somewhere within the interval a to b. So in this case, we're no longer considering the possibility of having an infinite limit of integration. That was our kind of first type or group of improper integrals that we looked at. So let's assume that a and b are finite, but now consider what I have underlined in red, the possibility that we encounter discontinuities of the integrand. Again, there are several ways that that could occur. So to begin with, suppose the discontinuity occurs exactly at x equals a, so the leftmost point of your interval. So if the only problem is at x equals a, then we're going to treat just that as a limit. So let's write this. I'm going to hold off filling in the limit. So we can apply the FTC where the function is continuous. So we could put in a placeholder, let's call it t, and we can evaluate the integral from t to b as long as t is to the right of a, right? So the only problem is that x equals a, so to the right of that up to b, there should be no issues. So what we want to do is evaluate the integral involving t, and then we're going to let t approach a from the right. And again, it's from the right because our interval has its leftmost point at a, so we're not really interested in what is happening to the left of a. So much like we've already talked with the other type of improper integrals, if this limit exists and is finite, we say that the integral converges. So that convergence idea has the same connotation. And again, otherwise, we say that the integral diverges. So looking at an example, notice here that 1 over x minus 1 has a discontinuity at x equals 1. So this falls into this category we're looking at here. If I want to look at this integral, we're going to treat it as we've defined here as the limit as t approaches 1 from the right, where we're going to integrate from t to 2. Now the antiderivative here is the natural log of x minus 1. Should say the absolute value of x minus 1. And we're evaluating this from x equals t to x equals 2. So we save the limit for the very last step. And so here we have the natural log of absolute value of 2 minus 1 minus the natural log of the absolute value of t minus 1. And we're going to send t to 1 from the right. Now, if you think about the natural log of t minus 1, so first of all, that's going to be the natural log function shifted over 1 unit. So it's going to look, maybe I should put it like this. It's going to look like this, but it's going to cross at 2 instead of at 1. And notice that as I head toward 1 from the right, this is going to approach minus infinity on the y-axis in terms of its output value. So this part here, it's problematic in that it's heading toward minus infinity. And so because of that, we're going to see that this limit does not approach a finite value. So maybe I should be a little more detailed. The integral consequently diverges. So as we might expect, dealing with a discontinuity at the right edge of the interval is pretty much a symmetric idea. We're going to take a limit, and we're looking at the integral here from a up to t. And as long as t is to the left of b, we can apply FTC. And we're just going to let t approach b from the left. Again, if this limit exists and is finite, we're going to say that the integral converges. And otherwise, we're going to say that it diverges. So here's an example. In this instance, my integrand is going to have a discontinuity at x equals 3, the rightmost point in my interval. So when I work about evaluating this, I'm going to think of this as to the minus 1/2. this is going to be the limit as t approaches 3 from the left of the integral from 0 to t of 3 minus x to the minus 1/2. Now, when we're thinking about this, I will point out this would be a good situation for u substitution. I'm going to use that kind of off to the side to help me anti-differentiate. If u is 3 minus x, then du is negative dx. So what this is telling me is that my antiderivative needs to bring out a minus. So I can use the power rule on this, but I need to make sure that I include that negative sign. So the antiderivative here, consequently, is going to be, let's see, 3 minus x. This is now going to be raised to the 1/2, and I would divide by 1/2, but like I said, we've got to put that minus there. It would also be fine to be a little more formal and change the bounds to be in terms of u instead of x, but because I'm keeping this all in terms of x here, I can keep the rest of this consistent, and we're evaluating this from x equals 0 to x equals t. So in this instance, I can write this maybe a little bit more clearly. This is just negative 2 square root of 3 minus x. I think that's a little bit easier to read. So here, when I take my limit, we don't encounter the same problem we did in the previous example. So plugging in my bounds, I'm going to get negative 2 square root of 3 minus t minus a negative, so plus 2 square root of 3 minus 0. As I send t toward 3 from the left, the only thing that's going to happen is that this part's going to approach 0. And that's not going to cause any problems, so we're just going to be left with 2 times the square root of 3. So the limit exists and is finite. Consequently, we say that the integral converges. And further, we can say specifically that it converges to 2 square root of 3. So just because you have a discontinuity in the integrand, notice it doesn't, within the interval, it doesn't mean automatically that the integral diverges. It really depends on the nature of that discontinuity. And then we have to then consider the possibility that the discontinuity that the integrand has, I should say, is not at either endpoint, but somewhere in the middle. Let's call that C. In this case, what we want to do is kind of similar to the approach we took when we had an integral from minus infinity to infinity. At this stage, we know how to deal with a discontinuity being one of the limits of integration. So we can split this. So I have A to B, and there's a problem at C. Well, we can split this up into 2 separate integrals, one from A to C, and then one from C to B. And each of those individual integrals will have C as an endpoint or a limit of integration. So we're going to be able to break that in 2 and treat each of those using definition 1 and definition 2 respectively. So the integral from A to C is going to have a discontinuity at the right endpoint. So we can write that then as the limit as t approaches C from the left of the integral from A to t f of x dx plus the limit as t approaches C from the right of the integral from t to b of f of x. And of course, you don't have to use t on both of those if that's confusing, but just some kind of structure to writing that there. To be clear, this is because we're splitting it up as the integral from A to C plus the integral from C to B. And what I've written in black is how we defined those respectively. So we've got two integrals, or two limits, if you will. So just like we saw in the previous video, we can only say that this integral converges if both of the integrals on the right converge, meaning both limits individually need to exist and be finite. If either one of them does not exist or is infinite, we can stop and say that the integral diverges. So we have to be careful with the notion of convergence and divergence when more than one limit is involved there. And so we really want to specify this is a quality that has to be true about both of them. So here we have a discontinuity of 1 over x squared. That's discontinuous at 0, which is not an endpoint, but it's within my interval. And I should point out, it doesn't have to be exactly in the middle like this example, but it's between -1 and 1. So in approaching this, the way we're going to do this is I'm going to, first of all, write this as the integral from -1 to 0 plus the integral from 0 to +1. Now, unlike the case where we had the integral from -infinity to infinity, in that instance, I said you could split it anywhere you'd like. But here you have to split it at the discontinuity, so there's no choice involved with that. So we're going to approach this first one as the limit as t approaches 0 from the left, integral from -1 to t, plus the limit as t approaches 0 from the right, integral from t to +1. So I'm going to now anti-differentiate. My integrand, that's x to the -2, so the antiderivative is negative x to the -1. So we have to be a little careful with these signs. So we're going to have negative 1 over x, where I'm going to evaluate that from -1 to t. So negative 1 over t minus negative 1 over -1 plus the limit as t approaches 0 from the right, we're going to have negative 1 over +1 minus a negative 1 over t. Okay, now right away, both of these limits I can see a problem, but like I said, it really only matters if you see a problem in one of them. So I have here 1 over t, well, negative 1 over t, and t is approaching 0. So that fraction here is going to blow up, right? So we're approaching 0 from negative values. Technically, you could see it's going to go to infinity. So what we have to do here is we have to be very careful with that. As soon as I see that that's not approaching a finite value, I stop and I say that the integral diverges. And I'll point out here, it just so happens that the second limit is also problematic, but even if this second one approached a finite number, it wouldn't matter. This is enough for me to stop and say that the integral diverges. If both of those limits approached a finite value, we would add those two values together and say that it converges to that value.